Welcome back to the IAQA Australia podcast, everyone. Today we have the first of a series of episodes where we will be revisiting some of the presentations from our previous speakers. Today we have David Karoly's presentation from our 2020 webinar event, Servicing Disasters in a Changing Climate. This was a very special event because while we had originally planned for an in-person conference, due to a very new virus known as COVID-19, we made the late decision to cancel and hold the entire conference online, and the rest was history. So this is the audio from David's talk. A full video recording with the slides and our Q&A session is available on our website. However, it is only available for IAQAA members, and it's also free. So if you haven't joined yet, I highly suggest you jump on and take a look at all the other free content available at iaaqaaustralia.org.au. Now, as I said, this is the audio taken straight from the video recording, so there will be some times when David is referencing some information presented on a slide. And while I had done some light editing to the clip, most of this is the original audio, so there will be a few of these along the way, along with some background noise and pauses. So let's get into it. Let me start by introducing our speaker, and this is David's updated profile from LinkedIn as of July 2024. David Karoly is a Professor Emeritus honorary at the University of Melbourne. He's retired at the start of February 2022 from CSIRO in Australia, where he was a Chief Research Scientist in CSIRO Climate Science Centre. He is an internationally recognised expert on climate change and climate variability. He's also a counsellor on the Climate Council Australia. Professor Karoly is available for communication and outreach services on climate change and its impacts through his business, Karoly AOS Consulting. Professor Karoly was the leader of the Earth Systems and Climate Change Hub in the Australian Government's National Environmental Science Program based in CSIRO from 2018 until the hub closed at the end of June 2021. He was a member of the National Climate Change Science Advisory Committee during 2018 to 2019. During 2012 to 2017, he was a member of the Climate Change Authority, which provides advice to the Australian Government on responding to climate change, including targets for reducing greenhouse gas emissions. He was involved in the assessments reports of the Intergovernmental Panel on Climate Change in 2001, 2007, 14 and 21 in several different roles. He is also a member of the Wentworth Group of Concerned Scientists. He was elected as a Fellow of the Australian Academy of Science in 2019. He was awarded the 2015 Royal Society of Victoria Medal for Scientific Excellence in Earth Sciences. From 2007 to February 2018, David Karoly was Professor of Atmospheric Science at the University of Melbourne and in the ARC Centre of Excellence for Climate System Science. From 2003 to 2007, he held the Williams Chair in the School of Meteorology at the University of Oklahoma. So enough for me, let's get into it. Here's David Karoly's talk. Thanks, everyone.
I'm going to sort of try to give a brief overview not only of Australian climate extremes, but global climate and climate change. But the first thing I'm going to do is to do a bit more like a background on myself. Claire, can you confirm that, first of all, you're seeing my slide and that you can hear me okay?
Yes, both are working well. Thank you, David.
Okay, thank you very much. So, look, when I first got contacted by Claire about this, I said, I don't know very much about indoor air quality, and why are you asking me to give a talk when my expertise is on climate variability and climate change on indoor air quality. And Claire, I have a feeling you first contacted me about this in 2019. At a time when we were, in fact, experiencing some of the most extreme bushfire conditions in Australia, and the smoke effects were only just becoming apparent in some of the areas. So I will talk about the weather and climate extremes in the spring and summer of 2019, but I also want to go back a little bit earlier than that. And I first got involved in, if you like, understanding climate variability and climate change when I was doing my PhD and graduate study, which was a very long time ago. I did my PhD in the United Kingdom. I'm a true blue dinky die Aussie. I came back to Australia and worked in a position jointly between the Bureau of Meteorology and CSIRO, starting in 1981, then went to Monash University for 20 years, then went to the United States for 5 years, then worked at the University of Melbourne for more than 10 years, before my most recent position, which is leading this research centre based at CSIRO between the Bureau of Meteorology, CSIRO and 5 university groups. Climate change research really started now more than 30 years ago. In 19, having done a lot of work on climate variability, a graduate student of mine said he had to remove the long-term trends in temperature from some observational data sets of if you like, weather and climate observations for the Southern Hemisphere. I decided to look at those with, if you like, an objective of trying to show that the patterns of temperature change in the Southern Hemisphere, particularly the vertical patterns of temperature change, were not consistent with what we would expect from increasing greenhouse gases in the atmosphere. And the only problem was, the more I looked at the data, and the more analysis I did, I found that the patterns of temperature change, the trends over the previous 30 years, were entirely consistent with the impacts of increases in greenhouse gases in the atmosphere. And while I had been seeking to test the so-called hypothesis of global warming and the role of increasing greenhouse gases, the evidence showed that that was the dominant cause of the warming in the lower atmosphere and in the changes, cooling in the upper atmosphere way back in 1986 and 1987. I published my first paper. Since then, I have carried out work on both climate variability, climate change, and in the last 20 years have focused on the impacts of changes in climate extremes, because the climate extremes are essentially where the rubber hits the road. The impacts of climate change are mainly demonstrated through the impacts of climate extremes, whether those are changes in temperature, changes in rainfall, changes in sea level, or changes in bushfires. And I'm going to talk about all of those. So let me see if I can go to my next slide. So what I'm going to do, I mean, as I was really talking about it, I was, the critical aspects that I'm going to focus on in terms of risks to human society, risks to infrastructure, and risks to ecosystems, as well as risks associated with human health, associated with climate change, are really the physical risks associated with the changes in extremes. But there's a second aspect that I'm not really going to cover in this, and there will be other major changes, both in indoor environment, in infrastructure, and in our economy, associated with the transition to a zero carbon economy. Because if we're going to address climate change in Australia and globally, if we're going to slow down the changes in climate extremes, we need to make sure that we transition to a zero carbon economy as quickly as possible. And I'm not going to talk about that really much at all. We can have some questions on that a little bit later on, but certainly I will be talking about the relative impacts of business as usual emissions of greenhouse gases versus the advantages of rapidly reducing greenhouse gas emissions. I'm going to talk about global climate and how it's changed, as well as changes in global extremes, Australian observed climate changes and changes in extremes, look at the climate of 2019 and the not only extreme bushfires, but extreme air quality problems outdoor and indoor, the changes in other extreme weather events, including extreme heavy rainfall and hailstorms in December and January of, December 2019 and January of 2020. And finally, I'll look at, well, what does the future hold? And I won't be using a crystal ball to look at that. So let me start by looking at the observed changes in the global climate, and I will be using my cursor to act as a pointer. And the first graphic on the left-hand side of this screen shows the global average temperature from 1850 right up till 2019. It shows data from, in fact, 5 different independent analyses of these data collected from weather observations on land and ship observations, as well as satellite data over the last 40 years or so. And you will see that in the most recent period, the last 50 years approximately, there is extremely good agreement between the different data sets. As you go back a little bit earlier, particularly from, say, 1880 onwards, there are some years for which the different data sets and different analyses give slightly different results. But typically the uncertainties in the modern era in some of these data sets is of the order of less than 1/10 of a degree. If we look at the most recent 5 years, since 2015 and onwards, we find that the last 5 years on average show global average temperatures above 1 degree Celsius above pre-industrial levels. And all these temperatures shown here are done as a difference from 1850 to 1900. So there has been pronounced global warming of the order of 1.1 degrees Celsius over the last 100 years from 1900, superimposed upon substantial year-to-year and decade-to-decade climate variability. And we can see that decadal variability with a slight slowdown in the rate of warming in the period from 1950 to about 1975, rather more rapid warming from 1900 to about 1940 or so, and then most recently, quite rapid global warming. If we look at the graphic on the right-hand side in the lower panel, this shows sea level rise. And the first thing we notice in this graphic, over the same time scale, essentially 1880 to 2018, actually, no, in this case, it's only 2015, but it's essentially the same for the most recent period as well. We have seen a pronounced increase in sea level of the order of 20 centimeters up to 2010, and it continues, sea level continues to rise at approximately 3 centimeters every decade in the most recent period. And that sea level, if you look at it, shows much smaller year-to-year variability and is a much more steady rise. Sea level rise is primarily due to the expansion of ocean waters as well as the melting of ice on land. And the melting of ice on land includes melting of glaciers in alpine areas together with the melting of the Antarctic and Greenland ice sheet. And the two contributions, the melting of ice on land and the expansion of the ocean waters as they warm, both contribute about equal amounts to this long-term sea level rise. But projections of future sea level rise shows that the dominant contribution to sea level rise over the next 100 years and beyond will primarily be due to the melting of the Greenland ice cap as well as melting of ice in Antarctica. Now, I'm also going to talk about the contributions of increasing greenhouse gases and recognize that in this, if you like, graphic that I showed previously, all I've shown here is the long-term warming trends and the increases in sea level. I have not discussed what are the possible causes. And yes, there's been a lot of work done on showing that, in fact, the dominant cause of the increases in temperature and the changes in the global climate is due to increases in greenhouse gases in the atmosphere. And I'll show evidence for that in a few more slides. But let me first of all show why we know that human activity is the dominant cause of the increase in greenhouse gases in the atmosphere. And many of you will have seen graphics showing the changes in greenhouse gas concentrations. And this top right-hand panel is one of those graphics. It shows over the last 1,000 years and a little bit longer, the changes in greenhouse gas concentrations from ice cores in Antarctica, and then the most recent record over the last 30 to 40 years is in fact direct observations of carbon dioxide concentrations from Cape Grim in the far northwest of Tasmania, which is a baseline air pollution monitoring station. And we can see that for almost all of the last 1,000 years, the greenhouse gas concentrations were fairly stable at around 280 parts per million until something dramatic happened around 1800. And since 1800, there have been very rapid and, if you like, exponential increases in the concentration of carbon dioxide in the atmosphere, primarily associated with increases in the emissions of carbon dioxide from human activity, primarily due to emissions from burning fossil fuels, coal, oil, and natural gas, and emissions associated with the release of carbon dioxide from the decay of plant material associated with land clearing over the last 200 years approximately. Now, how do we know that these changes are associated with emissions from burning fossil fuels and land use change? And that's this second graphic. Because this second graphic, which shows, if you like, the mirror image or the reverse of the exponential increase of carbon dioxide, actually shows a exponential decline. That, if you like, mirror image of the exponential increase in carbon dioxide is the decline. And what this graphic shows is the ratio of the carbon dioxide isotope made up with carbon-13 compared with the carbon dioxide isotope made up with carbon-12 in the carbon dioxide. And this ratio of the carbon-13 to carbon-12 isotope has plummeted over the last 200 years. It was relatively stable. Normally carbon-13, and you can see that this is, if you like, a logarithmic scale, a linear scale of this ratio. But what we know is that carbon-13 is less common than carbon-12 in making the carbon dioxide in the air, but that the carbon-13 ratio or amount has dropped exponentially over the last 200 years. So why is that? Well, that's because through photosynthesis, when plants take up carbon dioxide through the stomata in their leaves, the lighter element, carbon-12 carbon dioxide, is preferentially taken up rather than the slightly heavier element, carbon-13 carbon dioxide. So the lighter carbon dioxide molecule, carbon-12 carbon dioxide, is preferentially taken up in the stomata of leaves as part of photosynthesis. And that means that any photosynthetically processed plant material, such as when land use is cleared of vegetation and the vegetation decays, will preferentially release carbon-12 carbon dioxide. And the fraction of carbon-13 carbon dioxide would fall. But in addition, what we know is that fossil fuels are actually fossilized plant material produced from the geological compression of plant material, particularly algae from oceans, as well as fossilized plant material in coal. And so coal, oil, and natural gas are essentially fossilized plant material. When they're burned, we can see very clearly that they're going to release more carbon-12 than carbon-13. And that's the reason for this plummeting of the carbon-13 to carbon-12 ratio. And it's a very clear demonstration that there has been a dramatic increase in the fossil fuel use, the land use change, leading to increases in the release of carbon-12 carbon dioxide from photosynthetically processed material. It is not carbon dioxide coming out of ocean waters. It's not carbon dioxide coming out of volcanoes, which are two common reasons that are argued by some of the, climate change commentators that appear frequently in the media, but is not based on scientific evidence. There is absolute certainty that the increases in carbon dioxide over the last 200 years are primarily due to human activity. And that this, if you like, is the most important graphic in the whole set of slides that I'm going to be using, because most people that are in the audience won't have seen this or won't be aware of it, I will assume. Now, it's also important to understand that not only is carbon dioxide important as a long-lived greenhouse gas, but there are other long-lived greenhouse gases that have been increasing due to human activity, including methane, nitrous oxide, and a lot of the ozone-depleting chemicals, the chlorofluorocarbons. And if we add the warming influences of those long-lived greenhouse gases, which have also increased rapidly over the last 100 years, and then work out what the overall influence, the overall warming influence of these long-lived greenhouse gases that have increased due to human activity, converted back into an equivalent amount of carbon dioxide. The carbon dioxide alone is now 410 parts per million in 2019. If we look at what the equivalent carbon dioxide, taking into account the warming influences of all the other long-lived greenhouse gases, we are now at 500 parts per million of carbon dioxide equivalent. The warming influence is as if we had 500 parts per million of CO2. That is nearly double the pre-industrial concentrations, which were effectively around 280 parts per million in pre-industrial times. So it's important to understand it's not just carbon dioxide, but other long-lived greenhouse gases that we need to consider as well. And if we want to solve climate change, we have to reduce the emissions, not only of carbon dioxide, but methane, nitrous oxide, and all the other long-lived greenhouse gases. So I've talked about increases in greenhouse gases. I've talked about the long-term warming that we've seen. When I showed the graphic on the increases in global average temperature, what I showed was that there'd been a global average warming of about 1.1 degrees Celsius over the last, 150 years or so, most of which had occurred since 1900. There have been a series of special reports by the Intergovernmental Panel on Climate Change as part of its regular updates on climate change science and its impacts. The Intergovernmental Panel on Climate Change was set up and produced its first report in 1990. Its most recent comprehensive assessment report was released in 2014, and the current one that's being worked on at present is another comprehensive assessment report, the 6th assessment report of the Intergovernmental Panel on Climate Change, and that won't be completed until late in 2021, more than 18 months away. But in between the 5th assessment report in 2014 and the 6th assessment report in 2021, there have been a number of special reports. And the one that's perhaps most relevant in terms of changes in extremes is the special report on climate change and the land. And I'm only going to talk about 2 of their summary dot points. And the most important one, in my view, is something that climate scientists have known about, and in practice nearly everyone knows about already, and that is that the land surface temperatures increase or decrease much more rapidly than the ocean temperature changes. And so we know that day-to-day temperatures in daytime heat up more rapidly over land than the day-to-day warming over the oceans. We know that in summer, the changes in temperatures between summertime temperatures over the land and summertime temperatures over the ocean are much greater over the land. And we also know that associated with climate change, the land surface warms up much more rapidly than the ocean surface. This point has been known for a long time, but what we usually talk about when we're discussing climate change are changes in global average temperature. We also know that effectively 2/3 of the global surface is ocean surface. And in practice, the changes in the land average temperature over the last 110 years or so have been rising nearly twice as fast, about 1 2/3 times as fast as the global average temperature. And this is a graph that I downloaded only 2 weeks ago from the National Oceanic and Atmospheric Administration website. Shows the annual average land-only temperatures. It's the average of temperatures only over the global land areas, including Antarctica and Greenland. But what it shows is that the increase in land temperature has gone from about minus 0.5 degrees Celsius on this scale right up to, effectively for the last 5 years, plus 1.2 or plus 1.3 degrees Celsius for the last 5 years. In other words, the warming globally on land has been about 1.7 times or 1.6 times the increase in global average temperature. So when we talk about the Paris Agreement seeking to limit global average temperatures to less than 2 degrees Celsius of global warming, what that means for people and land changes, and I have to point out, and maybe it's obvious, that most people are not fish and most people live on land, that what people will experience is essentially a warming of more than 3 degrees, which is the global land average temperature, even if the world limits global average temperatures to less than 2 degrees. So the warming for people is much greater. And then the second point is that these changes in global average temperatures are leading already to increases in the frequency and intensity of extremes. And these changes in extremes are impacting agriculture, impacting terrestrial ecosystems, and also impacting human health. So this is a summary snapshot, a graphic of changes in climate extremes from the last assessment report of the Intergovernmental Panel on Climate Change, from the 5th assessment report. But it's, if you like, a starting point summary. It's still very relevant and very valid for observed changes. And I'm going to start right here in the middle. There have been significant increases associated with the increases in global average temperature in more frequent hot days and hot nights, and more frequent heat waves and more intense heat waves over global land areas. There is also increases in marine heat waves as well that are having major impacts on coastal areas, such as on the Great Barrier Reef in Australia. With global warming, we're also seeing declines on average in the frequency of cold days and cold nights, and reductions on average in the frequency of frosts and cold extremes, which is good for human health. But the increases in heat waves are not good for human health and not good for air pollution. In addition, there are a number of other major changes in regions for which the large-scale circulation is leading to decreases in rainfall. There's been marked increases in droughts in the Mediterranean region, in West Africa, and also in parts of southern Australia, and I'll talk about that in a minute. But there have been, in fact, declines in drought in parts of central North America associated with increases in the average rainfall, and also declines in frequency of droughts in the far northwest of Australia associated with increases in the monsoon rainfall and the average rainfall in the far northwest of Australia. If we look at one-day rainfall extremes and even shorter 6-hourly rainfall extremes, we expect with an increase in global average temperature that the moisture content of the atmosphere will increase. We've seen observed substantial increases in the moisture content of the air on average. And if the air holds more water vapor, then when it rains on average, we're likely to get more extreme rainfall events, and particularly if those are associated with rapid rise of air, and that's exactly what we get in thunderstorms, and we have been seeing more intense thunderstorms, more intense 1 hour, 6 hour and 1 day rainfall events, essentially across the whole world. Not always, but generally across the whole world. So what about now if I look and focus in on Australian climate change? And what I'm going to start by doing is looking at the average temperature changes across Australia. And I think I've used up about half an hour of my time, so I'm going to move a little bit more quickly on some of these things. We see for Australia, this is the annual average of across the whole of Australia of the maximum temperature. And these are shown as departures relative to the 1961 to 1990 period. What we see is that 1991 here set a new record high for the average annual maximum temperature across Australia. 2013 was the previous record high, and the increase has been 0.5 degree in the most recent 6 years in the average maximum temperature. That's even faster than we would expect in 6 years for the global average temperature. And yes, there have been some rapid increases in extremes. What we see is that, in fact, much of the Australian average temperature shows large year-to-year variability, but no substantial increase until we get to about 1950. And since 1950, there's been an increase in Australian average temperature of about 1.5 degrees or so since 1950. Much the same sorts of magnitude, because Australia's obviously land, that you would have seen over the global average temperature increased by this sort of, if you like, extra 1/3 to 2/3 amount. When we look at rainfall, while the increases in temperature over Australia have been fairly uniform across the whole country, and all observation sites across Australia have seen increases over the last 100 years, the patterns of rainfall change are very varied. They vary between geographical regions over Australia, and they vary between seasons. And I'm going to first concentrate on the left-hand panel in the cool season, or the wintertime rainfall dominated region. And what this graphic shows is the 20-year average rainfall departures for the April to October, or cool season rainfall domains. And what we see is that these 20-year anomalies are shown as decile plots, comparing the 20 years from 1998 to 2017 to all other 20-year periods since 1900. And the dark red here and over Western, or the southwest of Western Australia, as well as in Victoria, southern Queensland and New South Wales, the orange colour is the lowest, the orange colour is the lowest 10 percentile, and the red is the record lowest rainfall. And we can see that this very low rainfall over the last 20 years has dominated the rainfall decline over southwest of Western Australia. And there have also been consistent rainfall declines in southern Queensland, the New South Wales coastal regions, and across most of Victoria. But if we compare those now to the warm season rainfall, the October to April rainfall for the most recent 20 years, what we now find is a completely different pattern. A little bit of a decline in Victoria in summertime rainfall over the most recent 20 years. But in fact, most of Australia, particularly the northwest of Australia, as well as the Northern Territory, what we find is record high rainfall in the most recent 20-year period through much of Western Australia and the Northern Territory. And it's either the record highest, or you can see on this sort of darker blue colour, the highest 10% of years. So more than half of Australia over the last 20 years in this warm season has experienced if you like, the wettest 10% of years. And in fact, if we look at the average rainfall across Australia on an annual basis, what we have seen, in fact, is an increase in annual average rainfall. And that's exactly what's been expected. Most regions are expecting increases in rainfall. If we look at particularly the tropical regions that are affected by monsoonal rainfall at present. So now let me look at some extremes. And as I've said before, there have been increases in hot extremes. And I'm going to use here some graphics from Victoria, because the Victorian government released towards the end of 2019 a new summary report on climate change science, or climate science, and particularly these graphics are very clear illustrations of changes in hot days. What this graphic is showing, and it's not as clear, is the definition here of an unusually hot day is days with temperatures above the 1 percentile relative to the normal temperatures in the whole year. And what we would expect, obviously, is across the whole year, 1% of days would be on average between 3.6 and 3.7 days per year. And that's what we're typically seeing from 1900 to about 1950. Year-to-year variability, but an average of about 3 to 4 days per year. And then after 1960, as the Australian average temperatures and the Victorian average temperatures have increased, we're getting a pronounced increase in the number of days, which relative to the whole 100 years would be 3.6 days. And we're getting the frequency of these very hot days in cases, a number of years where the extreme temperatures were more than 10 days, and in some cases as many as 15 days, exceeding the 1 percentile. In other words, if you like, 4 to 5 times as many days as you would expect occurring in the most recent period. Associated with very hot days is usually increases in bushfire weather, and shown here in this bottom graphic is the number of days with spring days with severe bushfire weather conditions, and that is fire danger index values above 25. Those are very severe bushfire weather conditions, and the frequency of these days is shown in this graphic for the springtime. And what we've been finding is not only increases in bushfire weather conditions in the peak of the summer season, but the bushfire season has been extending earlier into the spring, associated in southeastern Australia with hotter temperatures as well as decline in rainfall in the winter and in the spring. And that was demonstrated in that previous graphic, which was showing those very low rainfall or substantial rainfall declines in the most recent 20 years in the cool season, particularly in winter and spring. So let's now look at how we might, if you like, assess the role of greenhouse gases in driving climate change and changes into the future. I'm going to have to speed up a little bit more, but what this graphic shows is climate model simulations in this grayish band here for more than 30 different coupled ocean atmosphere climate models that are global simulations and then have grid cells over the Australian region of the order of 100 to 150 kilometres across. The grid cells exist all the way across the globe. These are global simulation that include the oceans and the land surface, include the atmospheric variations. They simulate the weather with a time step of 20 minutes, but they run from 1850 right up till the present period, right up till 2015 and into the future. And in these set of simulations, these had the increases in greenhouse gases that were due to human activity as well as other human influences on the climate. And shown with this, the continuous black line is the decade-to-decade temperature variations. And I should have pointed out that the model simulations included in this band include the results from more than 30 different models, but it's for the decade-to-decade temperature variations. It's not the year-to-year variability. And you can see the year-to-year variability in this wiggly line here. That's the Australian average temperatures varying year-to-year, and it's much easier to see the longer-term climate change if we look at the decade-to-decade average. And the decade-to-decade average agrees well with the model simulations with the increase in greenhouse gases. The temperatures are projected to continue to warm in the future. And what I'm going to do is show the comparison to climate model simulations, the same more than 30 different models, but now with no increases in greenhouse gases and just with changes, if you like, in the natural influences on climate, including changes in volcanic eruptions, as well as changes in sunlight from the sun. If we look at this blue band, what we see is, in fact, there hasn't been any long-term warming due to natural factors alone. There haven't been any increases due to changes in sunlight from the sun. There hasn't been any changes due to solar sunspot cycle or other solar influences. In fact, we can only explain this observed warming in Australian average temperatures and global average temperatures from the increases in greenhouse gases due to human activity. So we can completely eliminate other factors, and there is essentially no chance that the long-term warming has been due to natural factors when I'm talking about global average temperatures or continental average temperatures across Australia. And that means that the changes in extremes associated with the global warming and Australian warming can be directly linked to human influences on global climate as well. What about if we look at some of these other changes? This graphic here shows the Victorian average temperature, as well as the climate model projections from 1995 right up to 2030. And what we find here is that, in fact, the observed decadal increases in temperature over Victoria are tracking at the worst case of the climate model projections, extracting the data to essentially start in 1995 to use the climate model simulations from 1995 and then project the changes for 30 years into the future. And what we find is that the observed temperatures are tracking at the worst level of warming for the projections. And then if we look at observed winter rainfall, remember I said that it showed a decline, and there has been a substantial decline in decade-to-decade rainfall in Victoria in the winter season, and that is tracking at the worst case of decline in rainfall projected across the climate projections from the different climate model simulations. So both increases in temperature and decline in wintertime rainfall are tracking at the worst case of the model projections. Let me now skip to 2019. I'm going to pick up this and then I'll finish up in about 5 minutes. 2019, as I've said already, showed record high temperatures across Australia. We set a new record high, but if we look at rainfall over much of the period since 1910 onward, this is a trend in the annual rainfall, and we see an increase in rainfall together with large decade-to-decade variability. And if you're looking very carefully, way back, here we go, way back at the bottom right-hand corner, 2019 also set a new record low rainfall, not what you would expect due to climate change on average across the year, but due to natural climate variations. And what we saw in 2019 was extreme bushfire conditions associated with an extended drought that particularly had affected low rainfall in New South Wales, southern Queensland and Victoria in not only the winter, spring and summer of 2019, but also in 2018 as well. Repeated heat waves and periods of strong winds. And the combination of drought heat waves and very strong winds was essentially what led to the record high fire danger. We know that there were substantial natural climate variations associated with the Indian Ocean dipole, sea surface temperatures in the Indian Ocean, and a breakdown of something called the Antarctic circumpolar vortex that led to stronger westerly winds over New South Wales in the late spring and early summer period, as well as low rainfall and extreme fire danger. The climate change contribution was essentially associated with the increased risks of increases in temperature and increases in heat waves, as well as the reduced rainfall in the winter season across southern Australia and New South Wales that I've talked about already. So there is a climate change contribution, but natural variability was also a major factor in the extreme fire danger conditions. And then if we look at the fire danger across December 2019, again shown as a decile map for December of 2019 compared to the December seasons back to 1950 and earlier. So this is showing record high fire danger index across essentially the whole of Australia in December of 2019. The only region that wasn't a record high but was still in the highest 10 percentile was essentially much of Victoria. So if we want to look at the future, and particularly future changes in climate extremes, we have to look at different emission scenarios for the future. And I'm going to look at two emission scenarios. Essentially a business as usual emission scenario that leads to substantial increases in greenhouse gas emissions. And then another scenario, this blue one down here, which meets or seeks to meet the Paris Agreement commitments of limiting global warming to below 2 degrees or thereabouts. And note that this one has emission reductions of more than 50% by 2050 and zero global emissions or zero net global emissions by 2100. If we look at those in terms of temperature change and sea level change, we see that the rapid reductions in emissions do lead to a stabilization of global average temperatures in these set of climate models that were used in the 5th assessment report of the IPCC. This one has a low chance of emissions being greater than 2 degrees, the pre-industrial target. But remember that required global emissions to fall by 50% by 2050 in 30 years' time, and then fall to below zero to net negative emissions by 2080. If we look at business as usual, we get warming of more than 4 degrees as best estimate, but this is relative to 1986. The temperatures in the period from 1986 to 2005 were about 0.6 of a degree above the pre-industrial level. This uncertainty range in the climate models spans 67% of probability. So there's a 16% chance of temperatures being higher than that. That tick mark is 5.5 degrees above 1986 to 2005. Add 0.6 to that, and this is 6.1 degrees. There's essentially a 16% chance of global average temperatures under this business as usual scenario being 6 degrees above pre-industrial levels. And remember I said that we should look at land average temperatures. They would increase by about 1 2/3. That means 10 degrees of warming on land for that business as usual scenario. That would be catastrophic for agriculture, for natural ecosystems, and for human health. I'm now going to show, just because I wasn't scary enough already, a new set of climate model simulations from the Australian Community Climate and Earth System Simulator. It's a global climate model run with new representation of processes in the atmosphere. It's consistent with a large number of other global climate models that have been run specially for the most recent coupled model into comparison project and to feed into the 6th assessment report of the IPCC. Unfortunately, what we find now is that this climate model shows, in fact, global average temperatures that are substantially warmer than the mid-range estimate. And in fact, many of these climate models show substantial warming. And this shows nearly 6 degrees relative to 1961 to 1990. It shows more than 6 degrees of warming relative to pre-industrial. It also, in this model, it's the CM2 model that I'm looking at. The ESM 1.5 is the older generation of Australian climate model, and that shows warming which is more like the 4 degrees that I was talking about before. And what we find now is that the Access coupled model version 2 shows more than 2 degrees of global warming relative to 1961 to 1990, and in fact shows 2.5 degrees of global warming with the same emission scenario that was assumed to limit global warming to less than 2 degrees. What we find now is that nearly 30% of the latest climate models do not limit global warming with these rapid emission reductions to less than 2.5 degrees. I'm going to finish up now, and my time is pretty well completed with a few summaries of the projected changes in extremes. And I'm going to focus on these changes in extremes using this graphic that came out in 2016 from the Australian State of the Climate Report. And let me start by looking at the fire weather. Remember, in 2019, we had extreme fire danger conditions, and there were certainly some politicians and some media commentators saying that it was too early or not possible to say that climate change was a contributor to those extreme fire conditions. Here in a report that came out in 2016, and there has been studies way back since the late 1980s saying that climate change was going to lead to harsher fire weather conditions for much of southern and eastern Australia. And that's exactly what we experienced in 2019. Yes, climate change has been known to increase the risks of extreme temperatures and bushfires for more than 30 years in Australia. And the media communication in 2019 was completely inappropriate when it said that climate change was not playing a role. As I've said before, we have had, and we expect to continue to see, extreme one-day rainfall events becoming more intense, decreases in wintertime and springtime rainfall leading to increases in droughts, and increases in temperatures leading to more heat waves and fewer cold extremes. So let me now look at heat waves across many different areas through a number of different metrics. The first one here is the number of heat wave days in different regions, including for Australia and the Mediterranean region, but also here in South Asia and Northern Europe. And what we find, the scale I should point out across the bottom here, is the increase in global average temperature. So this is showing the change in heat waves associated with different levels of warming. The warming of 1 degree is essentially where we are at present, and that shows of the order of 20 heat wave days in that sort of current condition. But if we look at 2 degrees of global warming, we've got essentially a trebling of the number of heat wave days, even for 2 degrees of global warming. So what that means is that 2 degrees of global warming is not a safe level. It shows a very rapid increase in many of these extremes. The peak intensity continues of the heat waves, that is the, if you like, the additional warming in these heat waves continues to increase, essentially consistent with the increases in global average temperature and land average temperatures, with increases of 2 to 3 degrees, with global average temperatures increases of the order of 2 degrees. The most dramatic impacts in terms of changes in extremes, not so much impacting air quality, but certainly impacting buildings indirectly as well as directly, will be the increases in sea level rise and the increases in frequency of coastal inundation due to sea level extremes. And what we know, and the easiest way to look at this, is changes in the return period for a given sea level that has been associated with, for instance, once in 100-year extreme sea level events associated with storm surges, high tides, and long-term sea level rise. And so if we look at what that would mean for increases in sea level, the sea level is expected to increase at a minimum by a 0.5 metre sea level rise over the next 100 years, even if we rapidly reduce our emissions, and then to continue rising beyond that. For Williamstown, which has a sea level rise graphic, and much of Australian coastal areas have relative, if you like, return periods of sea level rise extremes rather like this, a change of half a metre in sea level rise will lead to a change of the once in 100-year period to increasing in frequency to essentially a once in every year return period. And that is, we're already seeing increases in sea level extremes, increases in coastal erosion, but these changes in extremes will affect all coastal areas. And it's not so much the mean sea level rise, it's the increases in extremes which are the most important factor. Okay, there's a summary graphic. I'm going to skip over the summary graphic because I want to get to the the question time. But what I do want to do is to point out that we have the highest confidence in changes in extremes in terms of the increases in heat waves, in sea level extremes, in severe fire weather, in reductions in winter rainfall leading to increases in drought in southern Australia, and in increases in heavy one-day rainfall. All of those extremes have been and are being observed at present, and they will continue as global temperatures increase over the next 50 years or so. And we know that under all future global emission scenarios, even if we rapidly reduce emissions, that future global warming will almost certainly exceed 2 degrees above pre-industrial levels by 2040. In other words, the warming we've seen will more than double over the next 30 years, and that even with rapid emissions, we are very unlikely to limit global warming to below 2 degrees. We might be able to then further reduce emissions, but we are unfortunately locked into global warming of at least 1.5 degrees and very likely 2 degrees. And even if we overshoot 2 degrees, it would require substantial periods of negative emissions, negative emissions from human activity to draw back the carbon dioxide concentrations so we could then reduce global temperatures back to below 2 degrees again.
So that brings us to the end of the talk. I'd like to thank you if you've listened this far. Thank you very much. And if you've got any questions, get in touch with us, admin@iaaqaaaustralia.org.au, and jump on the website if you want to see the rest of David's talk with all the slides and our Q&A session. That's available at iaaqaaaustralia.org.au. And again, that's free for members only. And if you can also find us on LinkedIn, that's #IAQAAPOD.